Okay, so finally we could start. We can start, and I'm glad. We are glad to have here the speaker, special speaker, the guest in person. He appeared. He is from Israel, professor from Israel, and he is the Ron Folman. Ron Folman, he graduated from in Tel Aviv. Actually, I would ask him to present himself because I know about him just from Wikipedia that he was born in Tel Aviv, and he also, I know, studied there, right? Or not? He correct me. I do not remember already. But I know also that he spent some time working in Germany and in Innsbruck and in Heidelberg. And now he is a professor at Hebrew University, right? And he is a leader of the chip, atom chip group. Ron, please, the floor is yours. Please introduce yourself, more, give us more information about you.
Thank you, Sasha. Is the microphone working?
Yeah, microphone is perfectly working. We
Okay.
just do not see you because camera is looking on the screen, and we can turn it. Mikhailo, could you turn camera so that we could see speaker?
Okay.
And tilt it a bit.
Okay.
Perfect. Yeah.
Okay, great. So thanks a lot, Sasha, for the invitation. And yes, as you said, I was born in Israel, and I spent quite a number of years at different institutes in Europe. I did my PhD at CERN, in the accelerator in Geneva. And after that, postdoc in Innsbruck with Anton Zeilinger, who got the Nobel recently. And after that, in Heidelberg, and then I returned to Israel already 20 years ago. Okay, so today's talk is about can a rock be a wave, as you see in the title. And we are actually now celebrating 100 years to De-Broglie, who gave us wave-particle duality, the French scientist who gave us the idea of wave-particle duality. And this seems like very old news, but today we are revisiting this whole business of wave-particle duality because of quantum gravity. We are trying for many years now to put together the two pillars of modern physics, which are gravity or general relativity and quantum mechanics. Both of these theories have been proven to be right by many, many experiments, but we have never found a framework to join these two theories. And now experimentalists are trying more and more in the lab to do experiments where these two theories have to work together so that we get hints on how to build a unified theory, which we call quantum gravity. Okay, so the technology in the labs is becoming better and better, and this allows us to think of these new experiments. And this is what I want to describe to you today, how these experiments are going to look like. Good. So what you see here actually is a rock. So when I say rock, I actually mean this. This is a nanodiamond. For quantum physicists, this is a big rock. Specifically, we're thinking of a nanodiamond that has a mass of something like 10 to the minus 15 kilogram. So this is about 10 to the power of 11 carbon atoms. Yeah. So imagine a nanodiamond which has 10 to the power of 11 carbon atoms. The size is about 1 micron. Yeah, that's the size. And what you see inside it is one spin. Yeah. So this is all C12 carbon atoms. They have no spin. but inside we put one contamination. This is in the form of this nitrogen atom. It's inside, and a vacancy. Vacancy means that there's no carbon atoms there. This nitrogen vacancy, also called NV center in diamonds, already known for 20, 30 years, has a spin. So if you put such a nitrogen vacancy center in the middle of the diamond, you get a spin just like it was if it was a regular atom. So this is this spin here, it's this nitrogen vacancy center, and we're going to play with this spin. This is the outline of the talk. Again, you see here the diamond that we're talking about. This is the same diamond that you saw before. And all our experiments until now were with regular atoms, specifically the rubidium atom that you see here. It's an alkali. So it's 10 to the minus 25 kilogram. I'll show you results that we have with the atom chip with these rubidium atoms. And now we want to jump to nanodiamonds, which are 10 orders of magnitude heavier. So the motivation, I'll give you the motivation for these experiments. As you already understand, it has to do with quantum gravity. Some reminder of what De-Broglie taught us about wave-particle duality and complementarity. And I'll explain to you about the Stern-Gerlach interferometer that we're going to use with these nanodiamonds. And what is the atom chip? I'll tell you a little bit what is the atom chip. And then, as time will permit us, I'll explain to you more details about the experiment. And that's it. And you can, again, in the website, find quite a bit of papers we already wrote about this quantum gravity experiment. Okay, so let's begin. Again, I have to change slides here. You want to change the slides? That would be great. Good. Thank you. Okay. So I will not talk about quantum technology today, but in the world, when people do quantum optics, they also do fundamental science, but many of us, most of the groups I know, also do quantum technology. So I just want to give you 2 slides about what I mean by quantum technology and what we do in our group with quantum technology. But this is not the topic of the talk, but I think it's also nice, especially for young people, that after that want to open up their own company or join another company to do quantum technology. So what kind of quantum technology do we do in our lab? We help the industry. The industry engineers come to our lab and we teach them how to do quantum technology. So first of all, we do clocks, compact cold atom clocks. That's how it looks like. It's a very small device. Inside there are atoms. You see here this red dot are atoms, cold atoms. This is a real picture from this pyramid. It's called the pyramid MOT. It's a magneto-optical trap. With laser light, only one beam coming in, we actually cool the atoms to microkelvin temperature. It's very easy these days to cool atoms to microkelvin temperature. So you don't need cryogenics at all. The whole thing is room temperature. No cryogenics. No liquid nitrogen, no liquid helium, nothing, just a laser. And this is a Nobel Prize of 1997, how to cool atoms with the laser. And so one beam cools the atoms to microkelvin temperatures. You can even cool them these days. People cool them to picokelvin temperatures, extremely low temperatures. Picokelvin, imagine, 10 to the minus 12 Kelvin. And after that, they hardly move. And then you can turn it into a clock. We do microwave spectroscopy. You have here a microwave cavity. And it does microwave spectroscopy with atoms. And this is the clock. And you have mu metal shielding against magnetic interference. So this is one type of quantum technology.
Ron,
Another type
sorry, Ron.
Yes.
I would ask here the question. We agreed, yeah, that we ask you question during the talk, right?
Sure, please
Yes.
Go ahead, ask.
So you said it's not the topic of this presentation, but
Yes.
Actually to understand more, I just you are talking about single atom or a cloud of a few atoms.
Yes. So typically atomic clocks are a cloud of, let's say, 1 million atoms, just to get a better signal over noise. But it's a very dilute gas, so that there's no interaction. So it's single atom physics.
It is in vacuum.
Of course, always
It
in
is
vacuum.
it is in vacuum in the optical trap. It's the optically formed potential, laser formed potential,
Well, it's
right?
actually called a magneto-optical trap. So there are also
Mm-hmm.
magnetic fields here. There are coils and also magnetic fields. It's called a magneto-optical trap.
Mm-hmm.
This is a very simple device that actually anyone can build it in a very simple lab. And it was first built already 25 years ago. And you need a coil and you need a laser, and you get these trapped atoms cold.
Mm-hmm. And
Yeah.
what makes them to use them as a clock? What is the frequency
Well, what
there?
makes them, it's a completely different lecture of how to build
Just in
clocks,
few
but
words.
just in a few words, these alkali clocks, cesium, rubidium, all of these alkali clocks, they have hyperfine splitting in the ground state.
Mm-hmm.
Yeah, this is electronic ground state, hyperfine splitting. These two levels are extremely narrow. And if they're narrow, you can use them as a clock by just looking all the time for the resonance.
Mm-hmm.
Yeah, the microwave is looking for the right resonance.
Yeah, because ultra
And,
cold. Okay.
and if you hit the resonance, then you know you're on the right frequency. We know the frequency of this transition in these atoms, alkali atoms, to many digits. And so if you have frequency, correct frequency, then you, of course, have also correct time.
Mm-hmm. Ultra cold,
This
it does not have Doppler shift, and it is
ultra cold is for not having Doppler shift and also
okay.
not having aging, because if you have hot atoms in some vapor cell, usually they collide, they create molecules, they create chemistry with a cell, vapor cell. Here, they don't move.
Oh, it's interesting. And what is the normal lifetime of this device? I mean this experiment.
Well,
How long it can?
you can use this clock for many years, because these
Really?
atoms, you collect them every cycle you do of the experiment. A cycle is, let's say, 1 second. So every second you
And
collect
then
this
you have
cloud
new atoms.
again.
Okay.
You have a new cloud.
Mhm.
Yes.
New
Yes.
cloud. Okay.
So
Thank you.
this is an example of a miniature cold atomic clock. By the way, cold atomic clocks is what gives us the GPS time, all the time that you have in your watches, in your clock, in your phones. This all comes through the GPS system, and it all comes from cold atomic clocks that are sitting in Paris or in Boulder, Colorado, in the US. Yeah, so it's all cold atomic clocks, but this is a miniature. Usually they're much bigger. This is a miniature cold atomic clock. And this is what one thing we built for the industry. Here, by the way, you see in this poster, even much better clock than this. This is a European consortium that we are part of. And now these cold clocks have moved from microwave transitions into optical transitions. And it's much more accurate. And so this is a consortium, European consortium, that is trying to move the timekeeping of the world from microwave frequencies to optical frequencies. And this will be 5 orders of magnitude more accurate. So even these cold atomic clocks, they have different levels of accuracy. Yeah. Okay. So that's all I'm going to say about clocks. We also help the industry develop magnetic sensors. Here you have a vapor cell. It's hard to see, but it's a vapor cell of warm atoms. Fiber going in, fiber going out. No electronics, nothing electrical, nothing metallic. And through this spectroscopy, you can tell what is the magnetic field. We typically use our knowledge in fundamental science for technology, and also our knowledge in technology for fundamental science. It's always a back and forth game. So for example, we built for the industry these magnetic sensors, but we're also using them, as I show next, for searching for dark matter. So we're part of an international collaboration. All these are magnetic sensors around the world, looking for these domain walls going through Earth, domain walls of dark matter. We use the same magnetic sensors for both industrial applications and for fundamental science. And this is an example, a paper that just appeared about our work on this dark matter. And by the way, you ask, what do people do with these magnetic sensors in industry? They want, for example, to scan the brain, to replace the MRI and the CT that are very big and expensive. the brain emits magnetic radiation, and they use these atoms in a helmet around the head to scan the brain in a much simpler, passive, much cheaper way. Okay, so these are just examples of quantum technology. Maybe next slide. We also use atom interferometry for acceleration sensing, which is very important because GPS is becoming very bad. There is hacking and jamming and spoofing of GPS, and people don't like the GPS anymore, and they want all future navigation to be on inertial navigation systems that are built based on acceleration sensors. And these atoms, when they're cold, they're also very good acceleration sensors. They're extremely sensitive to any kind of movement. Next. And these are latest two technology papers we put on the archive. You can find them. This is a chip scale Sagnac interferometer. This is for rotation sensing. For good inertial navigation, you need 3 accelerators for linear acceleration and 3 sensors for rotation acceleration under 3 axes. So this is one paper and another paper together with the American National Institute of Standards on how to do.
But what is sensor here?
What is the sensing? Well, when you have an atom, you ask how does it sense acceleration? Yeah. So you want to build an inertial navigation system. These atoms.
Rotation, especially interesting.
Rotation. Well, rotation is due to the Sagnac effect. In Sagnac effect, you have a loop. You take an atom.
I know about light, interferometer, photon.
And so the idea is how to make very small sensors with the Sagnac effect. So it means building an interferometer. Okay, so how do you build on a chip an interferometer that has a loop, and then you can sense the Sagnac effect for rotation? But really, I don't think we should go into that. You can read the paper because this is really not the topic of my talk. Okay. Okay. Maybe at the end, if there's time, I would be happy to describe it. So anyway, this is just to show you our 2 last technology papers. These are technology papers, quantum technology, and it's all coming from our understanding of fundamental physics. For example, this latest paper, together with NIST, is before we could use this, do this paper, we had to learn what is clock interferometry. That is taking a clock and splitting it into interferometer. One clock in 2 places at the same time. That's a clock interferometer. Take one clock, atomic clock, put it in 2 places at the same time. That's called the clock interferometer. We first published it in 2015, and then we had to learn how to measure geometric phase, like Berry phase, but also Pancharaton phase. They're very similar. And we published this 4 years ago, and only then we could know how to make the technology. In this sense, interferometric sensors for acceleration, for forces, and so on, what we call metrology. Okay, that's all I want to say. And maybe just to show you that our former students, you can move on, are going out and opening companies. So it's very nice to see our former students open all kinds of companies. This is the latest, Quantum Art. It's a company in Israel that does quantum computing with ions. And you have very good funding for these companies. And this is a company that does quantum computing with photons. All these companies, our students are part of them, and some other companies as well. Next. Okay, so now to the topic of our talk. This is an interferometer. What you see here is an interferometer. So many groups around the world are doing interferometers with atoms. What does it mean, interferometer with atom? You take one atom here, and you make 2 wave packets out of this atom, and they do 2 different trajectories in space, and then you join these 2 wave packets, and you measure some interference pattern. That's the idea of interferometer. So at least 2 trajectories that are split, an atom is split, or any object, but we do it with atoms. The state of the art in the world, by the way, the heaviest object in the world that people manage to split and see an interference pattern is a molecule with 2,000 atoms. That has been done in Vienna. And we try to go now much higher than that. But until now, we only did it with single atoms. So you take a rubidium atom, and I'll show you a result. You split it, you bring it back, you see some interference pattern, just like in the double slit Young interferometer. Okay, but now the idea is to put nanodiamonds in this interferometer. And why? What is the motivation? Well, next. First of all, you want to test quantum mechanics in new regimes. Quantum mechanics tells you that there's a superposition principle. You can split anything. You can split a car, you can split a spaceship, you can split a human being, put him in a superposition. Of course, in principle, no one has done it, yeah? But in principle, you can. But quantum mechanics, as I said, this superposition principle was only tested until now on molecules, heaviest objects, on electrons, on atoms, and on molecules, on photons, of course, but never on heavier objects. And now, first of all, we want to test quantum mechanics with these very heavy objects. Also, there are all kinds of extensions to quantum mechanics, like this CSL model. It's continuous spontaneous localization. These are extensions to quantum mechanics, exotic physics, you can call it, that people are thinking about, and we want to test them. So first motivation is quantum mechanics. Then there are exotic theories about new forces. There is, many people are thinking, theoreticians are thinking about a fifth force. These are all kinds of additions to existing forces. The fifth force usually is a Yukawa potential. It's a correction to gravity at short distances. We can test that. We can test interfaces between quantum mechanics and gravity, like this Diossi-Penrose collapse. People think that if we split a massive object into two places, each massive object creates a curvature of space-time. You know that according to Einstein, each massive object creates a curved space-time. But what happens if you take a massive object and you put it in two places? Are there two curved space-times? Are they in a coherent superposition? So this is exactly what Diossi, who is Hungarian, and Penrose, who's British, independently developed. They say that if you develop a superposition of curved space-time, it's very unstable and it will collapse quickly. And we can also test this hypothesis. And this self-interaction hypothesis, some theoreticians claim that these two wave packets will attract each other if they're massive, because of gravitational interaction. Although with every other force, we never saw this self-interaction. For example, if you take an electron, it's -1 charge. You split an electron, you never see electrostatic interaction between the two wave packets. You never see it in experiments. But people say gravity is unique. And in gravity, we will see interaction between the two wave packets. So this is called self-interaction. So there are many things we would like to test with this massive object in an interferometer.
Ron, may I ask a question here?
Yes, sure.
Actually, in all these experiments, I think there is no interaction because they work in regime when you have only one particle flying at one time, and then you wait, and then another particle is flying. So times or fluxes are so that you always have one particle on this way.
Well, in quantum mechanics, if you assume that you have only one wave packet, yeah, it's true that every time you have only one particle in the system, but you have two wave packets. Now you can say that these two wave packets are just a mathematical description, and there's no really two physical entities there or disturbances there. Well, many people think differently.
No, I mean, if you do not have interaction between splitted electrons, which Coulomb interaction is much more higher than gravitational interaction. Why do you expect to have gravitation interaction? It's interesting.
Well, because many theoreticians think, I don't want to go into it now, so I just say that many theoreticians think that gravity is unique. But I don't want to go into that. It's a whole debate. Okay, but many people think that gravity is unique in many ways, not just in the 40 orders of magnitude from the interaction force, but also unique in other ways. But this is why it's called exotic physics. You come up with crazy hypotheses, and now you want an experiment to test them. Okay? Okay. But I really don't want to go into that because we just don't have the time. And I want to show you the experiment. Now, the main motivation for this experiment is this paper that was published already 7 years ago And what these people say is the following. Let's say that you have one interferometer. This one interferometer is this interferometer. But let's say you put in parallel another interferometer. So you now have two interferometers at the same time. So you have 4 wave packets. And let's say that this interferometer has one nanodiamond. This is a nanodiamond. And this interferometer has another nanodiamond. So now we have 2 nanodiamonds. And now between these 2 massive nanodiamonds, as I said, 10 to the minus 15 kilogram, maybe this distance is 100 microns. You have a gravitational interaction here that is actually stronger if they're neutral than any other interaction, spin-spin or van der Waals or any other interaction that you have. And now you measure the spin. I told you that there is a spin inside these nanodiamonds. You do a spin measurement correlation of these 2 spins. And you do what's called in our language of quantum optics a Bell measurement. A Bell measurement is to measure for entanglement between the 2 spins. It's non-classical correlations. And if you measure entanglement here between these 2 spins, the entanglement could only come from this interaction here. And this interaction was mainly gravitational. And if so, people claim then only a quantized field can create entanglement. And so this would be first proof that the gravitational field is quantized. This is the idea of this paper. And this is, after all these motivations that we could do with a single interferometer, we would like to go for this motivation where we need 2 interferometers in order to measure this effect. Okay, next. But can we split? So the question is, can we split a large object? No one has ever done it. It's a big question. How do you split a large object? Next. So we go back to De-Broglie, and De-Broglie told us, well, there are several things you have to take care of when you want to try and split a large object. Next. By the way, you see his thesis was in 1924, exactly 100 years. So he taught us about complementarity, and you can write it in the following equation. This is wave-like, W is wave-like properties, and P is particle-like properties. It's a one-sum game. This goes up, this goes down, of course. This is complementarity. You can also write it as visibility of an interference pattern. Visibility means how strong is the oscillations in interference pattern. Yeah. And this is distinguishability, means you know which path. Yeah, when Sasha was just saying, but there's one particle there. This is called which path information. Do you know if the particle went through this path or from this path? This is called distinguishability. So if you have high level of distinguishability, you will never get visibility in your interference pattern. Either that or that. If you don't have any knowledge of which path information, you will get an interference pattern from your interferometer. This is a basic rule of quantum mechanics from De-Broglie, and we have to listen to that, and I will show you about this D. What are the different things, we call them D factories, what are the different things that create this D and kill our visibility? Now, why is visibility for us so important? If we don't see visibility, we have no proof that we had the coherent superposition of the nanodiamond. The only way experimentalists can prove that you have a coherent superposition, a quantum superposition of this big object in 2 places at the same time, is if you see visibility. We have no other proof. So it's very important for us to get high visibility, namely interference fringes. Otherwise, we have no proof, and we can say until tomorrow that we had a good coherent splitting, but we have no proof. And that's why we have to minimize this D. Okay. De-Broglie also said, De-Broglie also said many other things, but I'm not going to talk about it today. For example, he believed that quantum mechanics is incomplete, but I'm not going to talk about that today. Okay. There are many groups around the world, theoreticians and experimentalists, that are thinking how to split a big object. It's now a very hot topic. Yeah. For example, I show you some papers as an example. This just came out this year or last year, where they think of using optical potentials. This is from Innsbruck and Vienna. They're thinking of how to use optical potentials, and specifically, you see this inverted potential, where they try to use an inverted potential to stretch a wave packet of a particle until it breaks into 2 wave packets. This is their idea. Next. There is a group of Marcus Arndt. He holds the world record for massive object. This molecule with 2,000 atoms comes from his group, and he's trying to use all kinds of near field interferometers, also with optical gratings, to get this kind of splitting. And other groups around the world are trying the same approach. Next. And many more ideas that I don't want to talk about. This is, for example, an idea on how to entangle between atoms in a superposition and a pendulum, a big, massive pendulum. This comes from Berkeley in California, and many other ideas. People are searching how to split a large object coherently, quantum mechanically. Next.
Can you explain a bit more? I mean, we are speaking. You are speaking about cold atoms, which are in some form of potential, and you change this potential to have this two gap potential, or what is splitting?
The idea is eventually not atoms. The idea now is to take a massive object, at least 10 to the minus 15 kilogram.
Okay, does not matter. This is in this magnetic optical trap, yeah?
No. Magnetic optical trap is for atoms. Magnetic optical trap was developed for atoms. Now I'm not talking at all about the magnetic optical trap. Now I'm talking what typically people will do is take a large object, levitate it with some force, so it's in vacuum, levitated.
But levitated in some potential, but levitated
it's levitated in some potential. This object can be levitated in optical potential, in electric potential. It's called the Paul trap. In the diamagnetic potential, many people are trying to levitate. You have to levitate it.
Okay.
Then you cool it by some means.
Okay.
And then you try to split it into these two wave packets that I showed you. And these
modifying,
all these methods.
Working with this potential where it's levitated, levitating potential. What do you mean split? How to split? You make
That's exactly what I'm going to talk about. How to split. So I just quickly went through several ideas on how to split. For example, you put a potential that looks like a mountain. We call it an inverted harmonic potential. If you put one particle, one wave packet on such a mountain, it starts stretching. Because half of the wave packet falls to the right and half of the wave packet falls to the left. It stretches until it creates two wave packets. This is one example of how people want to split a large object into two. But today I will talk about another route. This is our way, which is different than what I showed in these papers. Okay, next. Now, what I want to show you is the route that we decided to take, which goes back to these two gentlemen, also 100 years ago, the Stern-Gerlach experiment. Okay. By the way, are you keeping time? How much time do I have? Because time is running, and I'm
actually we are free with time. You have unlimited time, so it's up to you. When you want to stop, you stop.
I see. Okay. Because I have a lot of material to discuss with you, and it just depends how much time or patience people have. Okay, so please feel free to ask questions as much as you want. So what is the way we want to split this object? What is our way to split this object? This goes back to these two gentlemen, Stern and Gerlach. Stern got the Nobel, as you know. This paper just came out recently. I think it was December 2023 in Quantum magazine. It's a very nice journal that with popular articles about physics. And they wrote a paper about 100 years to Stern-Gerlach. And at the end, they also wrote about our experiment to probe quantum gravity. So if you read this paper, at the end, you will see also a description of our experiment. Next. This is the original lab in Frankfurt. The building is still standing. It became a European physical, European physics historical site. And you can visit it. I visited there in the inauguration in 2019. It's a very nice place to visit. Next. Okay. And this paper came out in 2016, suggesting to use the Stern-Gerlach effect to split a large object. How do you do it? So this is time, and this is space. Now you take a large object. let's say this nanodiamond 10 to the minus 15 kilogram, and there's one spin in the middle. I showed you before this NV center. Now you put this spin in a superposition. Let's say it's a spin of 1. You put it in a superposition of -1 and +1. So the object is still one object, but inside the spin is up plus down. This is how the spin looks like. This we know very well how to do. We do it with RF radiation. We do it with microwave radiation. We know very well how to do it. People have been doing superposition of spin for a long, long time. Now, you apply, in T1, you apply a very strong magnetic gradient. So, spin up goes up. Spin down goes down. It's opposite forces. But the whole object is connected to the spin. It's carbon atoms connected to the spin through covalent bonds, very strong bonds. So where would they go? Well, if one spin goes up, all the carbon atoms will go up. If another spin goes down, all the carbon atoms go down. But in quantum mechanics, it's a coherent process, meaning both of them happen together. So in popular terms, the nanodiamond is now going in 2 directions at the same time. Yeah? That's the meaning of a coherent superposition. It just follows the spin, and if the spin is going in 2 directions, then it is going in 2 directions at the same time. That's why you have here, we call it wave packets, of course. That's why you have here these 2 wave packets. Now you reverse the magnetic gradient, they go back, and eventually they are joined into one object. And in this one object now, you can measure either an interference pattern, spatial interference pattern on a screen, like in a double slit experiment, or you can also look at the spin, and the spin also will show oscillations. In our experiment, it's easier to look at the spin, so we are looking for oscillations. Oscillations as a function of the time of the interferometer. Yeah, as the time is changing, or the potential for one of the wave packets is changing, you will see oscillations in the spin. Next. Okay, you already saw that this is the particle we intend to use. Next. And these papers are being published all the time. This started in 2016, and there are papers being published all the time, also this year, about how to use this kind of scheme, Stern-Gerlach scheme, for doing it. Next. Okay, so we go back to 100 years ago. This was the experiment by Stern-Gerlach. We all know it. And they saw these 2 lines. This is the original result. This, by the way, from a postcard that they sent to Bo, who was in Denmark. They didn't have internet. They sent everything by postcards or letters. So this was the original results. Now, the question is, in your textbook, when you learn undergraduate studies, it tells you, well, you had a superposition of spin up and spin down, just like I described before. And so that's why you got 2 beams. The screen collapses the superposition. Either the atom, they use silver atoms, either it's on the bottom or it's on the top. But until the screen made a collapse, they were in both trajectories at the same time. That's what the textbooks describe. Okay? But there was never ever any proof. I told you the only proof of a coherent superposition, the only proof is seeing interference pattern. To see interference pattern, you have to join the 2 wave packets. Only then you can see an interference pattern. But they never did it. They didn't have the technology to do it. They never joined them. So here was the screen. They never joined the 2 wave packets. And so they could only see these 2 lines. And so it is not proof of coherent superposition. So many theoreticians for the last 100 years, they claim that Stern-Gerlach did not have a coherent superposition. Okay? Could you just go back to the... Yeah. They did not have a coherent superposition. They actually had a beam of silver atoms, just like what Sasha said before. Half of the atoms were spin down. They went down. These, they went here. And half of the atoms had a spin up. They went up. And this we call a statistical mixture. And it's very different from every atom split into both directions simultaneously. Very different. So one statistical mixture is classical beam. Half of the atoms have spin down, they go down. Half of the atoms spin up, they go up. This is not quantum superposition. Quantum superposition means each atom is coherently split, which means it's at the same time in both trajectories until there is some collapse at the screen or the measurement device. Very different. So the first thing we wanted to prove is that Stern-Gerlach splitting, coherent splitting, is possible. No one knew if it's possible or not for 100 years. So next, we started to do experiment in 2013. The first experiment we did is Stern-Gerlach splitting, just simple like double slit experiment. Yeah, we published it in 2013. This is the result. These are atoms. These are atoms. After they go, we not have two slits. We just had the gradient that I showed you before. Yeah, in a minute I'll describe. So we just had spin up plus spin down, and then we applied the gradient. Atoms went in two directions, and then we joined the two beams and got this beautiful interference pattern. Yeah. The next thing we did is we took a clock, not an atom, but an atomic clock, and split it into two places and brought it back and saw an interference pattern of these two clocks. I won't have time to go into details. We also measured a geometric phase, like the Berry phase, the Panchratnam phase, and so on and so forth. This here is already a measurement. This is time, and this is spin population. So here it's a spatial interference pattern. Here it's a spin oscillation. Both of them are proof that there is coherent splitting. Okay, so this just showed us in the last 10 years that indeed Stern-Gerlach's coherent splitting is possible because we see an interference pattern. Next.
What's the time scale?
Here?
Yeah.
Here it's a microsecond. So this is like 70 microseconds. Yeah. These experiments, by the way, they all take place. Thank you for the question. They all take place in less than a millisecond.
What is the object here? What splits?
All these results, thank you for the question. All these results are with rubidium, cold rubidium atoms. These atoms are about 1 nanokelvin temperature.
Mm-hmm.
So actually they behave like waves according to famous De-Broglie equation of H over P equal lambda. Okay, so this is how.
So even is this Stern-Gerlach experiment? It is for cold atom. It is not that they are just flying and making just.
No. This is not for not with a beam like Stern-Gerlach did 100
not
years
with
ago.
beam. Okay.
This is starting. I will show exactly, but this is starting. I'll show you a picture in a minute, but this is starting with very cold atoms, standing at one place. So how do you
it is time.
do
okay,
it?
I understand. Yeah.
This is time, and this is one coordinate, one spatial coordinate. You take an atom, let's say spin up. 2 is the internal spin state. You apply an RF, radio frequency pulse. Yeah, maybe megahertz frequencies or maybe gigahertz frequencies. This is pi over 2. We call it pi over 2 operation on the Bloch sphere. You have spin up plus spin down inside the atom. One atom inside the atom, like that.
Pi over 2, it is analogous for light. For light, when you have this polarization, it's analogous of linear to circular polarization, or?
Pi over 2 on the Bloch sphere, it's analogous to if you have horizontal and vertical polarization in light. It's analogous to superposition of them.
Yeah, so it switched to circular polarization then.
Well, it depends on the relative phase, but usually the right description is just on the Bloch sphere. North pole is one state, South pole is another state.
Yeah. Okay.
And pi over 2 is just 90-degree rotation from the North Pole to the equator. That's a perfect coherent superposition. So here we had a spin superposition. We applied here a magnetic gradient. These purples are magnetic gradients. So start splitting in space. It starts splitting in space. Up goes up, down, spin down goes down. Different forces, opposite forces. And now we have to mix the spins, otherwise they're orthogonal and we will not see any interference because they give you which path information. I told you this means distinguishability is 1. We have to kill distinguishability. We do it by mixing them. So you cannot distinguish with the spin between the two paths. And then another one stops the relative motion, another magnetic gradient. and then we let them expand. All wave packets always expand, they overlap, and they give us these beautiful CCD images of the interference pattern. Yeah, this is with the BC, Bose-Einstein condensation, very cold atoms. This is with warmer atoms. This is maybe nanokelvin. This is maybe microkelvin. Yeah.
I'm curious how you collect the statistics. So it's
Well, you start with a cloud, actually. These are single atom physics, but you start with a cloud of maybe 10,000 atoms. So you get it in one shot.
It
a very
is
good question,
picture
but
of
you
one
get it
shot. It's not
one
you
shot.
accumulate it with time, but it is one shot you see. Okay.
One shot. Yeah. Because it's very nice because you start with a cloud. It's a very dilute cloud, so they don't interact. It's single atom physics, as I said, but you get in a single shot, you get the whole interference pattern. Now, you could do the same thing here. This is not good for the nanodiamonds. This is good for rubidium atoms, but not for nanodiamonds. Why? Because you need a lot of time for these wave packets to expand until they overlap and give you an interference pattern. Why is long time? Long time is maybe a few milliseconds. Why is long time very bad for nanodiamonds? Because nanodiamonds interact strongly with the environment. For example, black body radiation. They emit black body radiation. Or they scatter with black body radiation that comes from the walls of the vacuum chamber. And the decoherence rate is very fast. So you cannot have a long, millisecond is already long. You cannot have a long interferometer time or long experiment. They will, the decoherence will kill your experiment and you will not see an interference pattern. And so you have to do something much faster. And much faster means this. We call this the half loop, and this we call the full loop. Why? Because we have these two gradients like here. These two gradients are these two gradients for splitting and stopping the relative motion. But now we reverse the magnetic gradient. A third magnetic gradient accelerates them back very quickly in a few microseconds. And now our last gradient stops the relative motion. Why do we have to stop the relative motion? Because even the momentum is a which path information. So if you don't zero the relative momentum, you have distinguishability and you will not get an interference pattern. You have to erase any kind of which path information. So this is the duty of this last magnetic gradient. And now you do a measurement. You do a measurement, but of spin, and you see these oscillations as a function of the time of the interferometer. This is time again. Yeah. Okay, so now you have proof either from spatial interference fringes or from spin oscillations that you really had a coherent quantum superposition, meaning that until the collapse at the measurement device, you had the particle was in two places at the same time. This is what we are calling a coherent superposition. Okay, next.
Okay,
So one question. So
how do you do this spin mixing in here? You just do another RF pulse, yeah?
Yeah, so another RF pulse, this pi, every time you see a pi over 2, it just means another 90 degrees. So if you hear it was 1 means North Pole. Sorry, we said, let's say 2 means North Pole, 1 means South Pole on Bloch sphere. So if now you had 1, you apply a pi over 2, it goes from the South Pole 90 degrees to the equator. Also from the North Pole 90 degrees, it's to the equator. So we take both of them to the equator. This is just the equator. Coherent superposition on the equator. And then this magnetic gradient, the 1s are thrown out, different forces, and the 2s, it's a little bit of technical details here. I won't go into it, but this is what happens. Okay.
Okay.
Next.
One question
yes.
about this distinguishability, as you call it, right?
Yes.
And so it became worse when time became longer, right?
Yes, distinguishability.
Anyway.
It's a very good, very delicate question, your question. Distinguishability can come from two places. One, from our measurement, we can measure and get which path information, and then we kill the coherence of the superposition. So distinguishability can come from our devices, but distinguishability can also come from nature. Nature also conducts measurements all the time. This is called environmental decoherence. If there's a coupling to the environment, always there's a coupling to the environment, for example, through black body photons. And they measure the system all the time. And if you allow enough time, they will kill the coherence of your superposition.
So as longer this particle are splitted, as slower this amplitude here, right?
So the longer the time of the interferometer, the more time the environment couples to it and kills the coherent superposition. Yeah. Also, by the way, the bigger the splitting, it's easier for the environment to identify which path. So it depends on many parameters. Very complicated.
Okay, I understand. I can understand.
Very complicated to calculate actually the exact decoherence rate for many different processes and coupling to the environment.
How do you estimate the size of the splitting in centimeters?
Well, this is just Newtonian forces. Newtonian forces tell us exactly. We know the gradient, and so you know the interaction, magnetic interaction is mu dot b, and so the force is just mu dot gradient of b. We know it's Newtonian physics. We know exactly the trajectories.
Yeah, but what is the size of the splitting?
So size, typical size is a few micrometers.
Few micrometers. Okay.
Yes, typical size.
Okay.
Yes.
So for diamond should be order of magnitude smaller.
So for diamond, depending, we want to get also micrometer, but it's much harder. Yeah. I'll show in a minute some numbers.
Yeah,
okay, so this is the half loop and the full loop, and with the diamond, we will go for the full loop, much shorter interferometer, much shorter time. Okay? Now, for those who want to see this is an artist view, of course. It's not a real picture. It's an artist view. And we actually made this because some journal wanted to put our experiment on their cover. It's going to come out in a few weeks. So they asked us an artist view of the experiment. So this is what we did. So what you see here, of course, everything is in vacuum, so an ant cannot live there. But anyway, this is just for scale. So an atom chip can be a few millimeters in size, but the actual structures that do the gradient are very, very small. They're micrometer wire, micrometers cross-section micrometer. These are the wires here. Now, what you see here, it's called an atom chip, as you see. Now, when we run a current through a wire, high current density, you get very strong magnetic gradients. So we start here with very cold cloud of atoms. I said maybe nanokelvin. This is all by laser cooling. Everything room temperature, everything at room temperature. The whole chamber, the chip, everything is at room temperature. Very easy experiment. No cryogenics. No shielding.
Ron, could you briefly
What
repeat
about
the
shielding,
question?
temperature shielding?
Just a minute, there's a
Just
question. There's a question, just a minute.
This question, what about shielding, temperature shielding? Because we have a very big temperature in room and infrared energy come to your clothes and heat your clothes from
Yes,
room.
so our atoms, you mean the atoms?
Yes, yes.
Yes, this is what I call black body radiation. When I talk about black body radiation, I mean photons coming from thermal radiation, from warm object. Yes, even this is room temperature, very close to the atoms. You don't even have to think about the vacuum chamber, but this is room temperature chip, very close to the atoms. Here, the distance may be a few micrometers of vacuum.
Yeah.
The coupling is because they're neutral atoms, the coupling is very weak. So we have with atoms, we have seconds before it hits them up. With atoms, with nanodiamonds, much shorter, but with atoms, we have seconds until thermal photons coming from this room temperature manage to heat up these atoms. So no shielding needed. It's very surprising. You're right, very surprising. No shielding needed because the coupling is so weak. Coupling very weak. Okay? So we cool them with laser to nanokelvin temperatures. They can be nanokelvin temperatures for seconds without heating up. Very surprising. You're right. And then the first action that we do is we do inside these atoms. We do spin up plus spin down, as I showed you before. This is what I call the pi/2 pulse with RF radiation. So these atoms already have spin up plus spin down. Now we push a current, so there's strong magnetic gradient. And so some atoms push, like with this, there's also gravity, of course. This is in free fall. We release them from the trap, they're in free fall. So some atoms get here, those with the spin up get here. Some atoms with the spin down get here. But the important thing is that each atom is here and here at the same time. This is what the meaning of coherent splitting is. How do you prove it? How do you prove it? You bring them together, as I showed before. You have to bring them together to one wave packet, and then they organize themselves in an interference pattern. This is a beam, a laser beam, and this is a chip of a CCD camera. This is how we get the pictures. Yeah. So they organize themselves in an interference pattern. This is the only proof that experimentalists in the world have that the atom was here and here at the same time.
Is it really
Each
that
atom.
gravity makes a difference?
Gravity does not
mean,
make any difference. The only
no,
reason why we use the free fall is that if we
that
hold
free
it,
fall, that free fall is due to gravity.
yeah, free fall due to gravity, very, very weak
Unbelievable.
free fall.
I
But
thought
the
I thought that other forces, for example, just interaction with all environment, just electrical forces will be some dipole forces, dipole electrical forces will be too stronger, much more stronger than gravity.
well, electrical forces you don't have because they're neutral. They're neutral atoms.
Neutral,
Yeah,
but dipole, okay, okay.
yes,
I understand.
but dipole it depends with what. But anyway, you're right that there could be all kinds of other forces, but gravity is not important. That's why you don't need to compare to gravity. Gravity is not important.
I mean,
but
free
anyway,
fall,
we see them fall very close to G, to 9.8 meter per second square. So other forces apparently do not affect them. But gravity is not important here. This is not an experiment about gravity. This is just an experiment to show that there was coherent splitting here because we got an interference pattern. So this is the first experiment that was published in 2013 that showed, after 100 years, that Stern-Gerlach splitting can be coherent. Okay? That was the aim of this experiment. Okay? Yeah.
Picture is interference. What is the distance between neighboring maxima? Is it related to the De-Broglie wavelength? And how long is it?
Yes, so it's a very good question. What is the distance here? So typical distance, as you see here, can be very large. Yeah. So from here to here, it's 100 micron. So this is for us very large. CCD or optics can see up to 1 micron distances. So it's very convenient in terms of optical imaging. And what determines this periodicity is several issues. One of them is the size of the splitting. This is just if you look at a light interference pattern through a double slit experiment, which we learn in our undergraduate studies. Also, the periodicity of the interference pattern comes from the distance between the two slits. Exactly the same here. So the splitting that we put here is just like the distance between the two slits in the Young double slit experiment, and it will determine the distance, the periodicity between the fringes. Okay. The De-Broglie wavelength that you mentioned is also extremely important, and I will talk about it more later. Yeah. Okay, next.
Okay, 1 moment.
Yeah.
I'll post the question. Here's a second microphone. Yeah. You can ask it, and it will be heard on the recording.
Okay, so now we felt we are ready for the nanodiamond experiment. We had 10 years of experiments with rubidium atoms. All the results I showed you were with rubidium, cold rubidium atoms. And now we felt we were ready for the nanodiamond. But now a lot of theory had to be done. Yeah. But before we went, and I'll show you some theory that we did on the nanodiamond experiment, what we call feasibility studies. But before we did all this theory, now 4 years of theoretical papers on this experiment. It's a very complicated experiment. Before that, there's still things we needed to learn about the rubidium experiment. So first came this theoretician from Ulm in Germany, and he taught us something we didn't know. He taught us that in 1927, again, almost 100 years ago, there was a guy called Kennard, and he published this paper where he said the following. If you do this full loop Stern-Gerlach experiment, like we did, you're going to get a very interesting, unique phase accumulation law. What is phase accumulation? These oscillations that I showed you, this is really relative phase, a change of the relative phase between the two wave packets. So if the relative phase is 2 pi, you get a peak. Relative phase is 1 pi, you get a minimum. So the relative phase just tells you where you are on the oscillations. And so how fast is this phase accumulation? How fast does this work? So usual atom interferometers, there is something, an atom interferometer called the Ramsey-Bordet. It goes like t to the power of 1. T is the time of the interferometer. Another one called Kasevich-2 goes like t to the power of 2. These are the atom interferometers used in the world. But what Kennard said, that this Stern-Gerlach interferometer is unique, and it will go like t to the power of 3. So this group, theory group from Ulm, they calculated exactly this t to the power of 3 that theory expects. And this was a very important test to see if our interferometer is really a good interferometer, if it follows theory. And so they supplied the theory, what you see here, the theory that they supplied, and you see our data points. And this was really proof. It goes perfectly like the T cube. This was really proof that our interferometer follows the quantum theory of this expected for this interferometer. So this was very nice to see this agreement with the theory so that we really understand this new type of interferometer that was never done before. Next. But we thought it was just a technical issue, this t to the power of 3. We didn't think it was very important. But then came, a year later, this paper from Penrose, Nobel laureate Penrose, got the Nobel a couple of years ago. And he said, this is not just some technical detail, this is fundamental. What does he mean? He means that if you take a wave packet, this is a quantum wave packet of a system, this is a wave packet of the same system. The only difference is observation of the observer. One is in free fall, one is in lab frame. He calls it the Newtonian and the Einsteinian perspectives. So one is in free fall, the observer, one is in the lab frame. How do you see this wave packet, quantum wave packet? He calls it actually the quantum equivalence principle, because it's very similar to the equivalence principle from different perspectives of Einstein. And he says, well, this t to the power of 3 appears in the phase. And this t to the power of 3, he claims, is really the way to move from one frame, one description of the quantum system in one frame, to the quantum description in the other frame. So he claims this t to the power of 3 that we observed already is very fundamental. And next. And these people from Oxford, a year later, next, they suggested this experiment. This was, how do you test this? This was never tested because you need to observe the wave packets from falling frame and from lab frame at the same time. It's a very hard experiment. No one knows how to do it. Always atom interferometers are in the same frame, one frame. So no one knew how to do this, to test this actually. But then came this paper, and next they suggested this picture that you see here in a minute. They said, okay, you can test this by doing an atom interferometer. We start, let's say, from here. And one wave packet, you split an atom into 2 wave packets. One wave packet, you keep it in the lab frame, let's say relative to the atom chip, same place, one wave packet. Other wave packet, you let it free fall. And then you measure the relative phase of these 2 wave packets, and you know exactly this quantum equivalence principle. The problem is that in a lab, we don't know how to take one wave packet that is falling, one wave packet that is staying up here, The only way to measure their phase, you already know what is the only way to measure their phase, relative phase, is to bring them back. You have to bring them back. We don't know how to do it in the lab. No interferometer, atom interferometer, knows how to keep one wave packet here, drop the other wave packet there, and somehow bring it back to measure interference, to measure this phase. The only way we know how to measure a phase is to bring them back and measure interference. So this was a very naive picture by theoreticians. And for the last few years, we've been thinking with rubidium atoms, how do we do this with rubidium atoms? And very smart students in the lab, they came up with the idea, this idea. Here is the one atom. You now split it with this pi over 2 pulse. You already know this pi over 2 pulse, but with some currents in the wires. Here's the atom chip that they used. You catapult one wave packet up into a ballistic trajectory. Yeah, going into a ballistic, that's free fall. The other one, it depends on the spin. The other one, you keep in a spin that is affected by magnetic gradient. So this is spin 0, not affected by magnetic gradient. Only in the beginning when you give it acceleration. This one is all the time affected by magnetic gradient, so you can hold it against gravity. And that's how, very close to the atom chip, one, they hold this. This is time, and this is height in microns. And so this one is almost perfectly at the same position. And this one undergoes this ballistic trajectory, which is free fall. And then they're joined, but it's not enough. I told you here, one has high velocity, one has 0 vertical velocity. You have which path information. You want to get any kind of interference, you have to have an overlap in space, in position, but also an overlap in momentum. So now this going very fast, this atom wave packet going very fast, you have to slow it down and stop it so there's full overlap in momentum. Only then you erased distinguishability, and only then you'll see visibility, as I showed you before. And so this is what they learned how to do. And next, just a few weeks ago, we got the first interference pattern from this interferometer. This is the first time such an interferometer is built. And we got this first interference pattern, and now they're writing a paper about it. So these are really preliminary results. Next. Okay, enough. I'm not going to talk about rubidium atoms anymore. We finished a whole 10 years, a whole decade of rubidium atoms. And now we want to really do the nanodiamond experiment. And indeed, most of my group now is working in the lab on the nanodiamond experiment. And if anybody, any of the young students here wants to do a postdoc in nanodiamond interferometry, quantum gravity, I'll be happy to hear about it. After you finish your PhD with excellence, I'll be happy if you come and do a postdoc, experimental postdoc in our group. So here is again the atom chip. The atom chip has 3 very strong advantages. One, very high magnetic gradient, by the way, 3 orders of magnitude better than the best coil you can find on Earth. The best coil is maybe at CERN. I was working at CERN. If you take just a wire, a simple wire, but because it's so small, micron by 1 micron cross section, you can bring your atom or your nanodiamond so close that the gradient is very, very high. Okay? So I just give you an example with 2 amps. If you come 10 microns from the wire, you get 4,000 Tesla per meter. Yeah? So very high gradients, and with the nanodiamond, we intend to push 10 amps, 1 micron distance, get 10 to the 6 Tesla per meter. You cannot get that with any coil that I know of, at least, okay? Any simple coil.
You need superconducting wire for this, maybe.
Big current for small cross section.
So you ask, what is the current? Well, 1 micron wire, 10 amps. Let's calculate. It's a good question. Let's calculate. So 1 amp for 1. This is 1 micron square. 1 amp for 1 micron square. 1 micron square is 10 to the 8 amp per centimeter square. You agree? So 10 amps is 10 to the 9 amp per centimeter square. Very good question. Gold holds for short pulses something like 10 to the 7 amp per centimeter square. Room temperature gold can hold for short pulses, 10 to the 7th. So we need 2 orders of magnitude more current density. Very good comment. And so this is not going to be simple gold. Now you have wires that can sustain for short pulses 10 to the 9 amp per centimeter square. Not superconducting wires. These are wires that have actually embedded CNT. CNT is carbon nanotubes inside. So it's special wires, special materials. Very good comment. Thank you very much. So it's very high current density. You can get very high. Why do you need these very high gradient for the nanodiamond? Nanodiamond is big mass. The force on the spin has one spin. The force on the spin very weak. If you don't have very high gradient, you don't give enough momentum, you cannot split the nanodiamond. Just by sheer Newtonian force, you cannot split the nanodiamond. You cannot move it. So we need very high gradient, and that's where the atom chip is very good. You need very fast on-off magnetic gradients, everything in microseconds. Turn off, on, off. Coil cannot do it. Wire can do it, very low inductance. Even in nanosecond, we can turn on, off these very high gradients. And you have very high position accuracy because these wires are very accurate. You know exactly where the gradient is and where the atoms are. Very high accuracy of the experiment. Okay, so this is why we want to use the atom chip for rubidium and now for nanodiamond. Next. Atom chip. This is a picture when the atom chip was invented 20 years ago. It was invented. Actually, this is a picture, artist view of a picture of an atom chip. Again, these are the atoms. These are some wires. And this chip came from the group of Ted Hensch, who also got the Nobel Prize in 2005. Ted Hensch from Garching near Munich, from Max Planck. He's one of the inventors of the atom chip. So here you see an artist view. Again, vacuum, everything in vacuum. This is a few microns here. Here you see a real picture from our lab. You see all the electrodes, the wires, and everything. You can have microwave fields, RF fields, current carrying wires, so magnetic fields, electric fields, light fields. You can have on the atom chip all fields you want. Here you see the BC. This cloud is this cloud, yeah. And the reflection from the surface. The second cloud is the reflection from the surface. So the distance between these two clouds on the camera really tell you how high you are. Very accurate measurement of the distance from the chip. The distance between these two clouds. Okay. So next, 3 atom chips already made it to space. Yeah. So it's very mature technology. One is now doing beautiful experiments on the International Space Station, interferometry experiments. Yeah. Very beautiful experiments. By the way, these laser beams that you see are intended to cool the atoms. This is the MOT that I mentioned before. Typically, it needs several laser beams. In the clock, the miniature clock I showed you before, we just use one laser beam. But typically, it uses several laser beams. And here are the coils for the magnetic fields, anti-Helmholtz configuration. And here's the chip. So this is an International Space Station. This is the first one that went up in Germany, the DLR, the German Space Agency. What you see here is a vacuum chamber. Inside there is a chip. And this chip is making a Bose-Einstein condensation, BC, nanokelvin temperatures. This group, by the way, in Germany, in Hanover, they already achieved picokelvin temperatures. And this rocket went up and then went down again. And during the whole flight, it continued to make experiments. Very nice technology. And now I heard that the chip is also going up to the Chinese space station. Okay. And this is a brief history of the groups that invented it. And I was then with Anton Zeilinger, who also got the Nobel a few years back in Innsbruck. Okay, next. All right. So since we have a little bit of time, I want to show you the vision of the atom chip. So I showed you an atom chip that goes into a big vacuum chamber. But now the vision of the atom chip, because people want to use it for technology, it will go the vacuum chamber will be inside the chip, not the chip inside the vacuum chamber, but the vacuum chamber inside the chip. So what you have here is a silicon chip. This distance is 500 microns, like a normal silicon chip. You etch inside the vacuum chamber. It's a very small vacuum chamber. Pump is inside, some getter pump here. Particle source with some lead is here. maybe some MEMS valve between the bad vacuum and good vacuum, some integrated lasers for the light. This is the MOT I told you about before, magneto-optical trap with some permanent magnets, giving you don't need coils. And this is the area of the experiment. You get out the data through some fibers or some electronics. And these chips are already being built in several labs around the world. Yeah, you see here a structure from the UK, from Britain. And yeah, so this is a very nice vision for this chip. And many particles are being put on these chips now, not only ground state atoms like rubidium, like I described, but also Rydberg state atoms, also molecules, also cold ions, cold electrons. And now at CERN, they're even putting on these chips anti-hydrogen. So this would be the closest approach, because the chip is normal matter. But it's the closest approach ever, controlled approach between antimatter and matter. A few microns between them. Nobody knows what will happen there. And here you see some examples. We make actually chips for groups around the world. In my university, I built a fabrication facility that makes chips. Here you see two atoms trapped in a chip we made for Germany. And here you see atoms trapped with a permanent magnet chip. So no, not current carrying wires, but permanent magnets. They have all kinds of advantages. This is a chip we made for University of Amsterdam. Next. Okay, and there you can read in our website many papers about how these chips are built, if you want to build them yourselves. Next. Okay, nanodiamond experiment. How will we do it? This is the sequence of the experiment. First of all, you need a good source for nanodiamonds. How do you make a nanodiamond? It's very hard to make a nanodiamond, a good nanodiamond. Many companies already around the world are selling nanodiamonds, but they're very bad. They're very bad because there's no good control of shape. Each nanodiamond looks different. There's no good control of size. Definitely not good control of the material purity. Very bad nanodiamonds. There's no good company that knows how to sell nanodiamonds. Yeah. So we are going to build them ourselves. And these are the nanodiamonds. This is a chip. You see here, these pillars are nanodiamonds, very homogeneous, pure nanodiamonds. I'll show you a picture in a minute. So first of all, you need a good source of nanodiamonds. This is a schematic picture of a chip where there is a gap between two chips. It's two chips. It's a two-layer chip with a gap of 2 millimeters. And here we'll do the interferometer. The first thing we need, the first layer, is the nanodiamond source. Then these nanodiamonds are charged. We charge them. You do a Paul trap. Paul trap is a trap. Also, Paul got the Nobel Prize for learning how to trap charged particles. Any charged particle. It doesn't have to be an atom. So the nanodiamonds are charged, and here will be a Paul trap coming from electric fields from these ion chips. Ion chip here. We call them ion chips. An ion chip here. These are electric fields, AC electric fields that know how to trap a charged particle. This is called a Paul trap. Then you have to cool them. Why do you have to cool them? Because of the De-Broglie wavelength, or what we call sometimes the coherence length. Why? Now, this is very important. I told you that you have to close the loop. Otherwise, there's no interference pattern. But how good do you have to close the loop? Experiments are never perfect. How good do you have to close it? You have to make sure that your experiment is good enough, that your timing is good enough, that your currents are accurate enough. What is the number? So the answer is you have to close it as good, at least, as the coherence length of the object. What is the coherence length of the object? In principle, it's just the De-Broglie wavelength. So what is the De-Broglie wavelength of a large object like a nanodiamond? Very, very small. Very, very small. Yeah, because lambda goes like h over p, according to De-Broglie, and p goes like the mass. Yeah. So if your coherence length is extremely small, you have to close the loop with nanodiamonds. With atoms, it's very easy to get long coherence length. We cool them to nanokelvin, picokelvin. Coherence length of an atom is microns. That's easy for us to close the loop. But now you have to cool to get some coherence length. So for your experiment to work, you have to cool these objects to very low temperatures. Now, no one knows how to cool these objects. I told you before, we cool to nanokelvin and picokelvin with lasers because there's a good transition in the atoms. That's the Nobel Prize of 2001 of 1997. But with these nanodiamonds, very hard to cool with laser light. First of all, the transitions, because it's solid state, are much broader transitions. And second of all, the object itself is opaque. It's hard for the laser to go in. There's many reflections. Will not work. So laser cooling is out. On the other hand, we cannot cool with liquid helium or liquid nitrogen. Why? It's levitated. How do you cool something that doesn't touch anything? So we don't know how to cool it. But you have to cool it because of the Broglie wavelength. So the way we do it is the following. We call it feedback cooling. It's so primitive and it works. You need a very good optics, a very good camera. You now follow the object. It's in a trap, the Paul trap that I showed you before. So it's oscillating in the Paul trap. Now, if your camera and your optics and your electronics are you have high resolution of optics and your electronics is very fast, what you can do is you can follow the object, and every time you see, okay, now it's going in this direction, you give a kick by some force. If it's charged, you can give electric field kick, for example. It's going the other direction, you give a kick. That's why it's called feedback cooling. But you need really good optics. We call it homodyne measurement. Yeah, homodyne measurement can go way below the diffraction limit of optics. So if the diffraction limit of optics usually 0.5 micron or a few hundred nanometers, homodyne measurement can go down orders of magnitude below that. Yeah, to know where the particle is and what the velocity is, then you need very fast electronics. Otherwise, you miss the right time. Very fast electronics and a computer with a very good software to see what the optimized kick is. Yeah. So it goes through quite fast but quite convoluted software, mathematics, to give the right kick. It gives the right kick. You repeat it many times, and people have already managed to take this object, which is in a trap, and cool it down to the ground state. Yeah. The first paper came out, I think, 2021, cooling a massive object to the ground state of the trap. It's very hard. It seemed impossible. But just with feedback cooling, they managed to do it. Okay, so this is the first thing we're going to do to increase the coherence length. And this is this feedback cooling. This is going to happen here in the middle. Yeah. How much is? The ground state? Well, it depends on the frequency of the trap. Yeah, so we can't really talk about temperature. Temperature is not a good number there. But just take, for example, you can calculate yourself. A trap, frequencies of these traps can be, let's say, tens of kilohertz or 100 kilohertz. Okay, so you just take as the energy, you can take energy of harmonic oscillator, ground state is half h bar omega. Just put 100 kilohertz there, make equal K Boltzmann T, and you'll find the temperature, very low temperature, yeah, but it could be in the order of microkelvin, for example. Yeah. Okay.
Ron, I have noticed here in the chat there is a question from Andrei Dumik. Have you considered using penning trap since you already operate with high magnetic fields?
Yes, penning trap is a very interesting idea. Thank you. And people are considering to use penning traps. Well, there are advantages and disadvantages in each one, but people have made penning traps. It was a recent paper, I think, in Nature about penning traps on chips. So we might eventually use penning traps, but right now it looks like it's easier to use a Paul trap. Yeah, but the jury is still out. So thank you for this comment, but penning trap is definitely an option. Yes.
There was another question from Andrei. Why does, but that was half an hour ago, why does the frequency of population oscillations changes with pulse duration? Why does
the frequency of The T cubed. He was talking about the T cubed. This pattern of changing of this oscillation comes from the fact that it's t to the power of 3. If you just make a function that is t to the power of 3, you of course see that it will change the periodicity with time. Okay, so this is just an outcome of the t to the power of 3 phase accumulation law. Okay. Okay.
One more than question. Sorry,
Yeah,
from
no
me
problem.
as a stage. From my understanding, this let's say oscillator behavior frequency depends on the second derivative of the potential.
Well, now you're talking. Now you're
which you
talking about this
trapped in.
slide. You're
No,
talking about
yeah,
this slide.
about this try, about this
Okay,
slide.
about the Paul trap. Yes.
Yeah. But you do not say about this potential, yes?
The Paul
it
trap.
is crucial.
Yes.
Yeah.
Yeah. Let's say that it's a harmonic potential.
So it's
Okay.
harmonic potential, but you can tune it and to make its frequency maybe as low as possible or not?
Yes, but low is bad for us. I'll tell you why low is bad. For us.
Okay.
Low is bad. Low is bad for several reasons. One, always things try to hit you up. For example, we talked previously about a black body radiation, but there are many other, there's noise in the system, noise in the electronics, noise everywhere. Yeah, Nyquist noise, all kinds of noise. And if your frequency is low, the gap between the levels is small, and so heating rate is much larger. The lower the frequency of the trap, heating rate from the environment much larger, and you want to cool. You don't want a large heating rate to fight you.
Okay.
So this is one reason for high frequency. The second reason is trivial, where below a certain frequency, you can't even fight gravity. You can't levitate the particle. Below a certain frequency, it cannot fight gravity. Just take the derivative. The derivative is the force. It has to be at least like mg. Okay?
Okay, yeah.
Okay. Okay. So we said now, okay, let's now say we cooled it. So now we got the coherence length that we want so that we can close really good enough. By the way, this is something they don't teach you in undergraduate studies, most universities, but it's very nice. If you take a photon, just a Mach-Zehnder, a simple photon interferometer, it's the same thing. If one path of the light interferometer is a little bit longer than the other path, will you get interference pattern in a Mach-Zehnder interferometer? And the answer is very simple. It depends on the coherence length of the photon. So if the photons come together, but there's a distance between them on the beam splitter, the final beam splitter of the Mach-Zehnder interferometer, if this difference in when they come to the interferometer is smaller than the coherence length or coherence time, you can measure it in time or in length, the only difference is c, then you will get an interference pattern. And how do you get long coherence time or length of a photon? You want narrower frequency. In our language, it's just, or in the De-Broglie language, it's just colder and colder. But it's the same thing. Photons, atoms, nanodiamonds, all the same thing, just harder technology. Okay? Okay, so now we cool them. Now you have to neutralize them because otherwise they will interact very strongly with the environment, the coupling of the environment, so the decoherence rate will be even stronger. No chance to do the experiment. So we neutralize them. There are all kinds of ways to neutralize a levitated particle. So no electronics, all by light, UV light. We neutralize them, and then you can start doing the Stern-Gerlach interferometer that we did with the rubidium atoms that I showed you before. Everything done here. This chip holds the small wire with the current. So we call it the current carrying wire chip. After we cooled it and we neutralized it, we bring it to a distance of 1 to 2 microns from the wire that is here. We push this 10 to the 9 amp per centimeter square through the wire. And we look for the interference pattern as you saw with the rubidium atoms here below. And we repeat the experiment. with the rubidium atoms, we had the advantages of having 10,000 atoms at the same shot of the experiment. So we get an interference pattern. Here, no. Here, every shot of the experiment, only one nanodiamond. So we have to repeat the experiment hundreds and maybe thousands of times until we get a nice interference pattern. So the whole experiment has to be stable for a long time. Okay, now we recapture, as you see here, and we start the whole process again. What you see here are trajectories, simulated trajectories of the two wave packets of the nanodiamond. So this is time, let's say a very short interferometer up to 100 microsecond. And you see that a splitting can be here, it's only 50 nanometers. From here to here, it's only 50 nanometers. Yeah, this is about the size of the object. Yeah, it depends how many atoms you take. Yeah, in this case, we took an object that is 10 to the minus 19 kilograms, so it's about 50 nanometer in size, the object. Okay. Here is really a design of how all these layers go into a chip. You see here all the designs. And this is pretty much what I wanted to show you here. Next. And these are some preliminary technology experiments that we do. Here you see the double chip. This double chip is this double chip. So the interferometer is happening in this 2 millimeter gap. This is now being inside a chamber in Mainz, in the group of Ferdinand Schmidt-Kaller. So now he's practicing on ions. This is a picture of ions trapped here between the two chip in a pole trap. This is our special 1 micron by 1 micron wire that will take this 10 to the 9 very high current density. And these are the nanodiamonds that we are making. We are actually growing very pure diamond and inserting one NV center. Very hard material engineering, very hard material engineering. Yeah. Here we collaborate with many people, experts around the world. And so then we will break them when we need them. These guys are these pillars are these guys. And then we will break them by vibration. There will be a very weak layer here, a soft layer, a brittle layer, that it will be easy for them to break. And they will then be captured here because they're charged by the pole trap. So these are preliminary technology that we're developing for it. Next.
Sorry, I have a question. How do you manufacture those nanodiamonds with one?
With one? Yes, it's very hard, as I said, but you have two ways to do it. Not only with one, but in the center. If it's not in the center, very bad. Why? Because if it's close to the edge, a lot of decoherence from dirt on the surface. Always dirt on the surface. Patch potentials, dirt, and so on. So it has to be one and in the center. The way we do it is we grow diamond, then very thin monolayer of nitrogen-enriched layer, and then another layer of pure diamond. And then you have this layer, then you can etch a pillar. You etch away a pillar, but you still have no NV in the center. Just a very thin layer of nitrogen, yeah? Now you come with a very high resolution beam, let's say from a transmission electron microscope. Has a resolution of 1 nanometer. You come through the sample, you hit this layer of nitrogen, and this can activate one NV center in the middle. So it's a long process, really, which is still not mature. Still a lot of R&D to do for this process to work. Next. Okay, also a big force that we have to take into account that we didn't have with atoms is diamagnetic force. Diamond has very big diamagnetic force, much bigger than with spin force. So spin, I told you, is mu dot gradient of B. And if you calculate, you see here. So this is force due to spin. So what you see here is actually acceleration due to spin. It goes down with mass, of course, because if you have with one spin, the force doesn't change, but the mass increases, so acceleration goes down. So Stern-Gerlach acceleration going down as we go up in mass. Very bad for us. Diamagnetic force is constant acceleration. Why? Because it's a function of the volume. So the force goes up as the mass goes up. Yeah, because it works on the carbon atoms. Diamagnetic force works on the carbon atoms. So we have a problem. We have some very strong force, much stronger than our Stern-Gerlach force. And so we are using this force actually. First of all, we make a very small splitting with the Stern-Gerlach up plus down that I told before, maybe nanometer splitting. But then we can already use through the wires, the same wires, we can create the diamagnetic force. Diamagnetic force is a function also of magnetic gradient. And we use this much stronger force, you see here the diamagnetic potential, to increase the split to microns. So this is nanometer with the Stern-Gerlach force, and then micron splitting with the diamagnetic force. So many different things to consider. Next. Okay. So now I showed you the technology we're going to use, and now let's go back to theory. What are the theoretical problems? And the theoretical problems are mainly to do with this D. So let's go back to this D that De-Broglie taught us and look at theory of this D. Okay? So I want to talk to you about three types. I call them D factories. What produces D? I call them D factories. Yeah. What produces D? Okay, so first of all, I bring you a nice picture of a full loop. This is a full loop. This is a picture from 1951 from a book by David Bohm, who was one of the great second generation, maybe, scientists of quantum mechanics. And he put this picture. It was with permanent magnets. You see here permanent magnets, but again, splitting 4 regimes, like our 4 pulses. Splitting, stopping the relative motion, accelerating back, and stopping the relative motion again. And the first D factor that I want to talk to you about has to do with time irreversibility. You say, what is the connection of time irreversibility? Well, next. The connection to time irreversibility is that when you look at the interferometer at 2t, let's say this is 2t, and this is t time t, this is time 0, this is time t, and this is 2t, you see actually that if you want the wave packet to be perfectly like the wave packet in the beginning, that means that you perfectly manage to recombine it. As I said, it's an issue of time reversibility. Why? Because this half of the interferometer has to be to perfectly undo this half of the interferometer. So it's a perfect time reversal operation. Okay? And this is very hard to do. Some people even say fundamentally impossible because of all kinds of theories of time irreversibility. So how difficult would it be to win over time irreversibility? Well, this was actually quantified. Next slide. So this is called the Humpty Dumpty effect. Why Humpty Dumpty? Because Humpty Dumpty was this British song about something that crashed into many little pieces. And no one could put it back together again. And the idea, why did they use this Humpty Dumpty name? Because the idea is that if you split an atom or any object into 2 pieces, you can never bring them back together again. So that's why they use this name Humpty Dumpty. And they quantified it in 3 papers in the 80s. This was in the 80s. But before that, Heisenberg, Wigner, Lamb, Bohm, Fermi, all the big names that you know from the first half of the century already thought about this problem. But the name was given in the 80s by these 3 gentlemen here. And this is the equation. So again, it's about the ability, technical ability, but some say fundamental problem of closing the loop. So I told you that we need to close the loop in momentum and in position perfectly. And this is the equation. This is visibility, or sometimes people call it coherence. It's the same, 2 names for the same thing. So visibility and coherence. This falls exponentially. Yeah, if you want to get a nice interference fringes, it should be 1. If you get 0, you don't see anything. So this falls exponentially if this delta Z and delta P are large here, these are experimental imprecision. Yeah, these are experimental imprecisions. Your experiment was not good enough. Relative to what? Relative to the coherent width in momentum and in position that I discussed before. That is just called the coherence length. Okay? So people have always said, the Bohm said in 1951, it would require fantastic accuracy. They did not understand what kind of technology we will have today. Even for an atom, they thought it was impossible. And we showed in the last 10 years that it's possible to beat this very hard law. Next. I add here, etc., because it's not just delta P and delta Z. Many other things you have to make sure there's no which path information left. For example, the shape and size of the wave packet. Let's say that we had two wave packets. At the beginning, they were the same shape and size, right after the splitting. But now they undergo different trajectories. They can change. They see different gradients. They see different forces. They see different accelerations. They can change their shape and size. And if they perfectly match, center of wave packet perfectly match with momentum and position, but it's different size, very bad. Because that's enough to create, in the language of quantum optics, bad overlap. If you do an overlap integral. So also other things like shape and size of wave packet you have to control to close this loop perfectly and not to have which path information. Next. And even you have to control the rotation. So this Humpty Dumpty in rotation, I'll explain to you what I mean by that. This was published by us last year, a theory paper on how rotation can give you which path information. So now we split this wave packet, nanodiamond, into two wave packets. But now because of different potential, different accelerations, they rotate differently. And this is which path information. You can measure this rotation and know if the particle went from here or the particle went from here. If you have that, you are dead. You never get an interference pattern. So it's Humpty Dumpty in rotation. And what you see here is contrast, or again, visibility of interference pattern versus omega t. T is the time of the interferometer. Omega is the rotation frequency that you have. And you see that it's going down. And there's a limit to what you can do. You can cool rotation, of course. People can cool rotation. And we intend to cool rotation. It's also a hard technological problem to cool rotation. But we have to cool rotation. But even if you cool rotation, there's a limit to what you can do, which comes from the uncertainty principle in rotation space. This is uncertainty principle, not in X and P, but in theta and omega. So there's a limit also there, what you can do. But in principle, what is shown here, this work was done by a theoretician called Yoni Yaffe. And what you see here is that if this graph is in position, and these are the two wave packets, you see perfect alignment, perfect closing of the loop in position and momentum. But this y-axis is in rotation. And you see that the two wave packets in rotation don't close the loop. So you have which path information. And so this shows you that Humpty Dumpty works even in rotation space. No connection to decoherence from the environment. If you put it in deep space, no decoherence, no photons, no nothing, still this kills you if your experiment is not good enough. And when we calculate the numbers for all these things, we see that we need to use not the best electronics in the world and the best lasers in the world and so on. We need to even produce things that are better than the best money can buy for this experiment to work. So a lot of technology is being developed, has to be developed for this experiment. Next. And of course, there is environmental decoherence. We talked about it before. For example, BBR, black body radiation. It shows you that coherence, again, or visibility, goes down very drastically if the separation is large. This is separation between the two wave packets. So for example, here you have 100 micron. At 100 micron, and depending on the temperature of the environment and the object, if you at room temperature, the red, you see already at less than 100 microns, a few tens of microns, you are already dead. And even if you cool the environment to 4K and the object itself to 4K, you cannot split more than 1 what you have here is 100 microns, and what you have here is, this is in meter. So what you have here is really a centimeter. So long before that, you're already dead. So this is black body radiation. Next. And the third is the most interesting one. This is the third D factory. And why is it interesting? This was calculated in Berlin by Carsten Henkel. He did the calculation. And it's the most interesting one because I think it's the most fundamental one. So what he calculated is the following. He said, let's say that there is no external environment, no coupling to an external environment. You manage to isolate your vacuum is perfect, and no radiation, nothing. Also, no Humpty Dumpty. Why? Because you made the best lasers and the best electronics and the best everything. So you managed to close the loop perfectly. No Humpty Dumpty. So you don't have Humpty Dumpty. That was the first D factory. You don't have external environment. That was the second D factory. But this, you cannot fight. This is the third D factory. And why can't you not fight it? Because it comes from within the particle. Now, what is it? It's the internal environment. We don't have it in an atom, but we have it in a nanodiamond. The internal environment are just the phonons. These are the phonon modes that Carsten calculated for a small object. And these many different phonon modes with different names. And actually, I didn't know all this theory about phonons. He had to learn a lot about phonons to calculate all these modes. And then he calculated the witch path information. If you could measure these phonon modes, these two wave packets, they have different phonons. They have to have different phonons. Why? I want to explain to you why. I take a nanodiamond. Now I have spin up plus spin down. Now I apply a magnetic gradient. I give a kick and they move, these two wave packets move to two sides. But note that this spin here, it's the only thing that got the kick from the gradient, so it moved relative to the carbon atoms. If some atom moves relative to the other atoms, it creates a phonon. The other one, exactly the same, created a phonon relative to the, because it moved relative to the carbon atoms in the nanodiamond. But they got the kick in opposite directions. So even though the excitation amplitudes are the same, I mean, the excitation probabilities are the same to higher phonons, the phase, the K vector, the phase is not going to be the same. That means that you have witch path information there. It's different. If you can measure the phase of the phonons, you can know which went that way and which went that way. And as we know from De-Broglie, if you have this witch path information, you are dead. And that's why he calculated this graph, very nice graph. It's just about to be published. This is the object size. And luckily, we are still very small, but people want to do much larger in the future objects. And this is the splitting delta X relative to the object size. And what you see, he compared it to the strongest environmental decoherence that comes from black body radiation. So these photons are black body radiation. These lines are black body radiation. And you see something very interesting. Here you cool them down from room temperature to 1 Kelvin, 10 millikelvin, 1 millikelvin. You cool them down. And of course, as expected, you see that the limits, this black line, for example, is here. Whereas this red line is here. It means that with the black line, you can get with much larger objects, much larger splitting. If you cool down deep. Yeah, that's known. That's not surprising. What is surprising is if you look at the dashed lines here, these dashed lines, these are coming from, these are the temperature of the phonons. Yeah. And what is surprising here is that these phonons, these give you these limits. This is unallowed. This is not allowed area. This is allowed area. These phonon lines, they give you limits where you can never hope to split an object. Why? Because if it's very large, it's massive, and you need a strong kick to separate it. A strong kick gives a lot of phonons, even if you start from 0 temperature. And this will give you witch path information, which will not allow you to have interference patterns. So people dreamed 100 years ago already. They said, quantum mechanics, in 1,000 years, we can split a car. We can split a human being. We can split a rocket, whatever. There's no limit. It's just technology, no limit. Give me money, I will split it. But he is saying, no, 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 you have fundamental internal problem. So this, you might win over this by doing all kinds of crazy materials. For example, a lot of material engineering, again, we'll have to go into here. For example, there are materials that are called phonon gap materials, phononic gap materials, where you suppress the phonons because you build all kinds of geometries, crazy geometries of these materials. And so there are all kinds of ideas how to bypass this. But still, it's a very, very hard constraint on any future splitting. But luckily for us, we're still very small in our experiment relative to this graph. And so we are still okay. Thank you. And of course,
Ron,
you need to know...
Ron, one
Yes.
question. Actually, I see that it's already not actual, but I then from my side. So this kicking off by pulse. If you make it harmonically or just you usually make you should not do it.
If you make it
very
adiabatic,
abruptly.
you mean? If you make it adiabatic.
Not adiabatically, but you have, let's say, some age, some frequency, and make it in such a way that your Fourier harmonics do not coincide with phonons of the phonons, with frequencies of the phonon spectrum.
You're exactly correct, Sasha. The Fourier transform is what you need to do of the pulse. That gives you what frequencies are excited. You're exactly correct. And Karsten did it and looked at different profiles. This A0, A1, A2, he calculated many of them, many different profiles, because we tried to find an adiabatic or even different frequencies for than the spectrum of the phonons. But we found that the phonon frequency is so complex in this object. Yeah, these are 3D objects that you will never be able to find a pulse. We tried many different pulses that the Fourier transform does not excite phonons. But it was definitely on our mind. It's simply such a complex object already in terms of phonons.
I thought they limited anyway by the Debye frequency. Therefore, you should be just above this frequency, something like this. But okay.
Well, there's a limit to what you can do technologically, yeah. But anyway, we definitely talk about it in the paper. Okay, so but we did not find any way to change the frequency or the shape of the pulse, and therefore the Fourier transform in order not to excite phonons. Okay, we don't think it's realizable. But maybe one day somebody will think of a smart way to do it. Next, okay, the last piece of thing that you must do is know how to work with the spin. I told you all the time we're doing with atoms. It's easy to do a pi over 2, pi, whatever on the Bloch sphere. It's very easy with atoms. But with this NV, you have to learn how to work with it. It's in solid state. It's a much more complex spin. You have here the Hamiltonian of this spin. It's a very complex spin with electronic spin and nuclear spin. And so you have to learn how to work with it. So for the past few years, we also learned how to do spectroscopy with this kind of spin. But now, because I know that people here are interested in superconductors, I want to show you something. The only thing I will show you today that has to do with superconductors. And that is the following, this picture. So after we learned how to work with this spin, we decided to play a little game to prove that we know how to work with this spin. This spin has here a B dot S. This B dot S is just Zeeman splitting. So if the spin does Zeeman splitting, the magnetic field affects the spectroscopy. And so what we did is a very simple experiment, but I like it very much. So I will take 2 minutes to describe it to you. This is this picture. We took IBCO, superconductor, yeah, liquid nitrogen. And we put on it a very thin layer of diamond, 2 micrometers. And so it's like a membrane. Diamond, 2 micrometers, you can hold it like it bends. It's like a membrane. And in it, we put a very thin layer of NVs by implantation this time, implantation of ions. And because it's so thin, you put it on a IPCO. IPCO has, the chip is curved, it has all kinds of the wires and so on. We want it to be very, very close to the IPCO wires. So this, because it's so thin, van der Waals really makes the diamond take the shape of the chip. And now there's NVs inside. So with a CCD camera, we look at the spectroscopy of these NVs. NVs emit as a function of this Zeeman splitting. So it gives you immediately a magnetic sensor. So what you see here is a single shot, not a scan, single shot from a CCD of vortices in IPCO, yeah, just by looking at the emission. The emission is in red photons, emission coming out of this diamond, yeah. So I think that just by, we wanted it for a completely different purpose, but I think that these NVs can also be used for as sensors for electric fields, magnetic fields, all kinds of fields. And there's some startup companies in Europe that are already using them as sensors for different things. Even in medical applications, in surgery, they say that they could sense different things. Even some claim cancer cells because they have a specific magnetic or electric signature. But anyway, or NMR signature. And anyway, we just did a little game here to show how these sensors can also be a probe for superconductivity. And I think it's a very nice sensor. Okay, so we learned how to work with these.
Just wanted to ask about time. So it's very fast, but I understand it optics. But anyway, it should be photograph. It has some exposure time. What is the character time? Could you measure?
Well, in principle, it all depends on the time here can be long because of signal to noise. If you want a signal to noise, the time can be long. So time can be, let's say, minutes. But if you, it's not because of the camera, it's because of signal to noise from these NV centers. But if you, and this was taken many years, quite a number of years ago, I don't remember when, 2018. Every year, people are getting better and better signal to noise. And so I think that in the future, you can make this, we just did it on the side, like a nice game. But I think that if you really dedicate yourself to it, you can get very fast pictures. So you can see dynamics of vortices, for example. Yeah. But I don't have numbers to give you. Yeah. But I think this picture was taken in minutes. Okay. So I think we can conclude. And first of all, I hope I convince you that De-Broglie, Louis De-Broglie and Stan Gerlach are far from completing their historical role. We still learn from them a lot. And we go back to their papers to learn a lot from them. And fully understanding their ideas on wave-particle duality and spin forces may enable us to create a verifiable spatial superposition of a massive object. Verifiable means you have to see an interference pattern and then test quantum mechanics, quantum gravity, exotic theories, all the things I showed you in the beginning. Now, I want to tell you that many groups are levitating these particles. Here you see from my lab, by the way. Here you see a nanoparticle levitating in a pole trap. You see the nanoparticle here. Many people are levitating these particles not for interferometry, not for these experiments at all. It's a new field called levitodynamics. Why do they do it if they don't want to do interferometry afterwards? They do it because even these particles, if you cool them to the ground state, as I told you with this feedback cooling that now people know how to do quite easily. So you cool them to this ground state, they find that they are very good for metrology. They're very good, for example, for sensing electric fields, for sensing acceleration, for sensing all kinds of things. So there are groups all over the world, and high-tech companies are now focused only on that, on levitodynamics. So this is a vacuum chamber, but you don't need very good vacuum. Interferometer needs very good vacuum, but this doesn't need good vacuum. So maybe you go down with a simple pump to 10 to the minus 6, 10 to the minus 7. It's very, very easy to load them to these particles. And you don't have it doesn't have to have an exact shape or an exact mass, and so you just buy some powder of particles from some company. And so this is a very easy experiment. What is harder is then to cool them to the ground state. But this is a field called levitodynamics, and if you're interested in this, you just follow it. I think it's beautiful experiments and nothing to do with interferometers. Next, yeah. Here I give thanks to all the different people that had groundbreaking results in this field. So if we succeed in this very hard experiment, it will be because of what they did. So for example, ground state cooling by feedback cooling, I already told you. These are two people that led the way. Other people did rotation cooling. Other people did nanodiamond manipulation with spins inside. And so many groups around the world are working on different aspects and teaching us different technologies that we need for this very hard experiment. And if you're interested about 1 decade, the 10 years of Stern-Gerlach interferometry with rubidium atoms, then this was put recently on this book, in honor of Otto Stern, the guy who got the Nobel for the Stern-Gerlach and other findings. And that's it. And before we say goodbye, I still want to show you some anecdote next about De-Broglie, something I like very much. And this is less known about De-Broglie. And this is my way of saying thank you to De-Broglie, not only because of his wave-particle duality, but also because of another thing. And that is De-Broglie thought, as I said, that quantum mechanics is incomplete. What did he mean by that? He believed that the particle exists all the time. And we think that the particle does not exist and turns into wave packets and is several places and simultaneously. It's just because we don't really know how to write the theory. So we have all these wave packets. And he thinks, no, there's only one particle. And he called his theory the pilot wave. So there are all kinds of potentials, quantum potentials, strange quantum potentials that make the observations that we see, like interference pattern. But the particle has just one location at each given time, which is different than standard quantum mechanics. He called it the pilot wave, but the pilot wave, he could not prove that it really works. He came up with a lot of contradictions. There were a lot of paradoxes, contradictions, and people did not like this theory, so he gave it up. He gave it up for many years, but then came Bohm. And Bohm in the 50s started to develop the theory again. He called it Bohmian mechanics, or some call it the Broglie-Bohm pilot wave. Doesn't matter what the name is, but the idea is that you have the particle is always a particle, but there's this strange potential called the quantum potential. And this potential always tells the particle where to go, for example, in an interference pattern, and then it makes the interference pattern. So each time the potential sends the particle to a different place and makes this interference pattern. Read about it on Wikipedia or wherever. It's very interesting theory. It's identical to quantum mechanics in the predictions. You cannot tell them apart. So what's the difference if they're identical in the predictions? The difference is that the language is completely different for the mind. So people say, oh, the language for the mind, what is it important? You know, it's the same predictions, we calculate. We don't need to learn about this Bohmian mechanics. We wanted to show, just as a nice game, that sometimes thinking with a different language in your mind brings up new ideas. Yeah, it helps your creativity. So we took this Bohm potential, which is very strange for us, this Bohm potential, and decided, let's think with this Bohm potential, what experiment can we do? And we wanted to see, it's like a psychological game, if it would create some creativity in our brain, and we think of an experiment we would not think with standard quantum mechanics. That was the idea. And so we set together some people, and we said, okay, let's say this Bohmian potential is something real, we can work with it, and what can we do? And we came up with this idea of countering the Casimir-Polder force. Now, what is the Casimir-Polder force? It's like van der Waals force in a little bit distance. So our atom chip, if we bring an atom or nanodiamond close, a few hundred nanometers from the atom chip, we feel strong. We see it in experiment. We feel strong attraction. And if we don't fight against this attraction, much stronger than gravity, it sticks to the surface, it's gone. We cannot see it anymore. We cannot see the atom. We cannot do spectroscopy, nothing. So we always fight, and that's why we don't get too close, because then the force is so strong that even with our magnetic potentials and so on, we cannot fight this force. But we said, what if? So you have the potential of Casimir Polder, very deep potential, close to a surface. What if we can make a quantum potential that is exactly the opposite? Looks exactly the same, just change of sign. If we can create such a potential, and Bohm taught us exactly how to create such a potential, we can erase the Casimir Polder potential. And then we can do an experiment. We can bring a nanodiamond or an atom very close to the surface. We would see that it's hovering there, no attraction. So this already gave us an idea, this Bohm potential, of doing an experiment that we would not think about before. But now, how do you calculate this Bohm potential? This is mathematics, but in principle, I'll explain it to you here in this graph. So Bohm taught us that to engineer, you have to engineer exactly the potential that you want. You have to engineer the wave function, the shape of the wave function of your quantum system. So what you see here on this axis is just the wave function, square. It's the black line. It looks like normal Gaussian almost, but notice these ripples here. They're ripples. So if you make a lot of ripples, you get out of them a Bohmian potential that looks like the blue. But this blue is normalized because it should go very high up. It's normalized, this you see here, this is the quantum potential times, it's normalized to the wave function. So if the wave function here is very small, it's normalized to it. So the quantum potential actually should have been huge here. And we made it, it's hard to see from this graph, exactly the shape of the Casimir Polder potential, but opposite sign. And so here we plotted the residuals, the quantum potential minus the Casimir Polder potential, and this is 0. And you see that the residual, what's left after you do this minus this, is extremely small. That proves that we could really engineer a quantum potential that looks just like the Casimir Polder potential, but with a minus. And now, if this is all this language is true, and mathematically it's true, again, it's just a different way of doing the mathematics of quantum mechanics. If this language is true, you can actually go and do this experiment. We didn't do it. This is a theory paper. But now you can go and do this experiment, put a nanodiamond or put an atom, and see that it's not attracted. So this is just a nice thing I want to say about the De-Broglie, that although, and Bohm in this case, that he gave us also other ways to think about physics. And in this case, we were able to show through this theory paper that really sometimes thinking in another language gives ideas for completely new experiments that otherwise we would not think about. So I wanted to show you this just as an exotic anecdote about how we try to think in different languages sometimes for new experiments. So this was published last year. Next. And I want to say a final note about De-Broglie. So this is John Bell, the famous John Bell. He was a theoretician at CERN. And he's the one that proved that there's no hidden variables, you know, the Bell inequalities in the 60s. He's actually a very famous guy that proved that you cannot have hidden variables in quantum mechanics or to explain quantum mechanics predictions. And he said this about De-Broglie. He said, "Long may Louis De-Broglie continue to inspire those who suspect that what is proven by impossibility proofs, all those who say, even mathematical proofs, that this is impossible and this is impossible and this is impossible, and there are many such no-go theorems, they're called, all that is proved by impossibility proofs is just lack of imagination." So this is really, I think, a beautiful sentence, that a tribute that Bell gave De-Broglie in terms of how great the imagination of De-Broglie was. And he taught us to have imagination also for us. Next. Okay, for all the experiments I showed you and all of the big work that has been done in the lab, of course, I have to thank the students and the postdocs. And some of them you see have moved on already to other institutes around the world, and some of them are still in the lab. And of course, many theoreticians that are working with us on this very hard topic of trying to do nanodiamond interferometry. And of course, the funding agencies. And thank you very much for your attention. Thank you.
Thank you very much, Ron, for so nice and really inspiring talk. I still sit here. Maybe people just who is online wants to ask questions.
Sure, I'll be happy to answer questions.
Who are not.
There's a question here, Sasha.
Okay.
There's a question here.
Then switch to the audience.
Yes.
The question about the nanodiamond experiment.
Can you hear that? Is that microphone working? Sasha?
Hello?
Yeah,
Hello?
we can hear it. We can hear it.
Okay, great.
Okay. Yeah, so the question is about the nanodiamond experiment, specifically about the connection with gravity. So you showed the example of rubidium atoms being catapulted by a ballistic trajectory, something like that. And it was supposed to demonstrate this accumulation of phase due to gravity, or
You can
this
just
thing.
call it phase accumulation due to. Yes, I'll repeat the question.
It's not working.
They said that they can hear it.
It's working. Yeah. Okay.
They said that they can hear it. Yeah.
Yep. So do you plan an analogous experiment with the nanodiamond too? And if so, how could you like factor in the gravity?
So, thanks for the question. So this trajectory with the rubidium atom that I showed that we did in the lab really in the last few days, this is a much weaker experiment than doing it with nanodiamonds. Nanodiamonds, because they really produce, they're so heavy, they really produce gravity, you know. And atoms, you can neglect the gravity that atoms are making. So I would say that it will not repeat this experiment probably with the nanodiamonds, because there are so many other experiments we want to do with the nanodiamond to take this exotic theory of self or superposition of curvature of space-time or quantization of gravity. So there are many other, I would say, much more hot experiments that we can do with nanodiamonds, and I don't think we'll repeat that. But even this experiment that was done with the rubidium tells us something interesting about gravity and quantum mechanics. Not that that gravity is quantized, but it tells us at least that gravity creates a very certain phase for free-falling objects. And this is the aim of this experiment. So to answer your question, I don't think we'll repeat it because we have a long list of other experiments we want to do with the nanodiamond.
No, thank you. But the question was more like about how do you plan to perform this experimentally, like with the nanodiamond, to include gravity in your measurements, meaning that like one diamond would fall or another would stay in place.
No, but we're not going to do it. So let me just thanks for this. You're asking me to clarify something that I'm going to do this. We don't care about actually external gravity in the nanodiamond experiment. Let me just go back here. So with the nanodiamond experiment, we're planning to do simply this thing here. This is what we plan to do with the nanodiamond experiment. We did it also with rubidium, but we're planning to do.
Right.
So we actually don't care about external gravity. It plays no effect in this experiment. So of course it's there, but it's just a nuisance for us. We don't care about it. What is the gravity that we care about here? Is the gravity coming from the own nanodiamond. That's why we need a massive object. We need here a massive object because we're going to do experiments that have to do with the self-gravity. So for example, this nanodiamond here creates some curvature of space-time. And if the same nanodiamond also exists here, it creates also curvature of space-time. This only a massive object can do. So if these are in a superposition, namely they exist simultaneously, some real object in space or some real perturbation in space, also you will have curvature of space-time in a superposition. This only a heavy object can do. Or if this exotic theory about self-interaction, that this is going to pull this gravitationally. Or the less exotic experiment with the two interferometers, where the gravitational pull from this nanodiamond is going to pull the other nanodiamond, yeah, and create entanglement between these two nanodiamonds. So we are really going here for experiments where the gravitation from the nanodiamond itself is what is important.
No, thank you. That clarifies the question.
That
Thank you.
clarified?
Yes.
Great. Thank you.
Yeah, actually, in continuation to this question, gravity would it is limited because at least limited by the size of the diamond, in a sense
Yes,
that you could not go closer. Therefore, maybe it makes sense to make rubidium atoms go much closer and just split it in two interferometers and put one beams or not beams but positions are very close to each other to experience more gravity due to shorter distance.
So Sasha suggests that maybe we can do these two interferometers in parallel with two rubidium atoms with technology we already have. Well, when you calculate it, you find that to get a gravitational interaction between atoms, that must be at least an order of magnitude larger than all other interactions. Yeah, you just don't have it. So with a nanodiamond, you can get it, that the gravitation is stronger than all other forces. But with an atom, we can't get that point. So
like spin-orbit interaction and all dipole.
So it's just a matter of numbers at the end. We would love it if we could do it with atoms, but we just don't have that specific point in space where the gravitational interaction is the strongest.
Okay.
I also have a question. What's the reason for sending the atom chips to space to conduct experiments without gravity?
Yes, so that's a great question. So this is called microgravity experiments. Actually, before they were sent to space, I should have told you that Airbus, the company of the planes, they had a plane specifically for these experiments with atoms. It was going in a parabolic trajectory. And students were on that plane hovering for some seconds during the experiment. So why microgravity? Now you can do it on the space station with much longer times. Why microgravity? Because if we're on Earth doing experiments and we want a long interrogation time, the longer the interrogation time, the more sensitive your experiment is. It's the same with clocks, by the way. You want better timing, you want long interrogation times. If you have, you want to do a 1 second experiment. If you are on Earth, if it's in free fall, it's already 5 meters. Yeah, and you want to do it cryogenic, and you want to do this and that, it's realizable. Yeah. So what people do, they say, okay, let's levitate it like I showed in some potential. But these potentials always have noise. So they perturb the system. So that's also bad. So people say, how can we avoid this huge falling on Earth? And on the other hand, not have potentials that are always noisy. From the noisy lasers, noisy electronics, and so on. They say only in space. Because then you release the trap, it doesn't fall. And so, for example, with the atom chip experiment, I showed you that it falls a little bit during a short experiment in this artist view with the ant. But in space, you can do a very long experiment next to the atom chip. It's not going anywhere. Yeah, so that is the main reason for doing experiments in microgravity.
Okay, thank you.
Question?
Yeah.
And the question, what about the interaction between magnetic moments on these two different branches of the...
Yes. So actually, there's a long list of forces that between these two branches that can interact. Or as I showed, actually, you're talking about two interferometers in parallel.
Yeah.
Yeah. So if I go back to these two interferometers in parallel, just to show the picture in the motive, yeah, these ones. Yeah. So you have many different forces acting here. And you have to really make sure, you're right, you have to really make sure that the gravitational force is by far the dominant. And there are many forces like van der Waals, Casimir-Polder, spin, you have a spin here and you have a spin here from the NV center, spin. You talked about magnetic moments, you have a magnetic moment. All of these, you have dipole, by the way, because even though they're neutral, the electric distribution, of electric charges may be non-homogeneous, so you have a dipole interaction, which is probably the strongest. Yeah. So they found, at least in theory, that all these forces, there's a whole table, all these forces at a certain very specific point can be lower by at least an order of magnitude than gravity. But for that you need extreme conditions. For example, the surface of the nanodiamonds has to be extremely clean, because any type of dirt on the nanodiamond would create a patch potential. Although the whole thing is neutral, but it would create a patch potential, and all this creates dipoles, and this is a very strong force. So the material engineering that would have to go into these nanodiamonds is really... but there is theoretically a point where gravitation would be strongest. Yeah.
That was the last question. Okay, let's thank Zeron.
Thank you very much. Thanks.
And actually, we plan to have some pizza.
Pizza, great.
Who
Great.
want to discuss maybe something?
Okay.
Welcome.
The gravity of pizza.